Welcome back. So far we have studied two principles of induction, mathematical induction and strong induction, both of which apply to the set of integers or subsets of the integers. Now in computer science, it is also very common to use induction to prove properties of recursively defined data structures and algorithms. So there's a third principle of induction called structural induction. So structural induction does not work on integers, but it works on objects. These objects have a structure that is defined inductively by a set of rules. Now remember, there are two sets or two types of rules. There are the base rules. These are the rules that just add objects to the set being defined without any assumptions or any hypotheses. And then you have the inductive rules, which build new objects and add them to the set using existing objects that are already in the set. So to prove that a property P holds for all the elements of a set that is defined recursively, we again need two subproofs. First, we need to prove that P holds for every element that is added to the set using a base rule. And second, we need to prove that P also holds for every element that is constructed by an inductive rule under the inductive hypothesis that P already holds for all the elements that are already in the set, those that are used in the construction of the new element. Now let's illustrate the principle of structural induction using the concrete example of the set of perfect binary trees that we defined earlier. So to prove that a property P is shared by all perfect binary trees, we're going to write a proof by structural induction, which means we're going to write two subproofs. First, we must prove that the property P holds for every one-node tree. These are all the trees built by rule 1, the base rule. And the second subproof is to prove that P holds for every multi-node tree. These are the trees that are built by rule 2. Now remember that in rule 2, we must first have a single node tree in the set and then two other trees, and we put those three trees together. The single node tree becomes the root, and the two existing trees become the left and right children of the root. So to prove that P holds for this newly built tree, we must assume that the property P already holds for the left subtree and for the right subtree. So I hope you see the similarity between strong induction and structural induction. Remember that in strong induction, we must first prove that the property P holds for the first few integers from a to a plus b. These are the smallest integers. And second, we must prove that the property P holds for the integer k plus 1, assuming in the inductive hypothesis that P already holds for the smaller integers, k, k minus 1, k minus 2, k minus b. Well, notice here in strong or structural induction, it's very similar. First, we prove the property for the smallest trees, those that are produced directly by the base rule. And second, we prove that the property P holds for the bigger trees produced by the inductive rules, assuming that the property already holds for the smaller trees, namely the subtrees we're using to build the new ones. Now let's write a proof by structural induction of a particular property P of the perfect binary trees. So let T be an arbitrary PBT. Let's use d of t as a shorthand for the depth of t. Remember that the depth of a binary tree is an integer that characterizes how tall the tree is, how many levels of nodes it contains. Remember that the depth of a tree increases by 1 every time you use rule R2. So what we're interested in this particular example is the total number of nodes in a tree. Let's denote that number, n of t. And the property that we are going to prove is the following. For any perfect binary tree T, the total number of nodes in T is equal to this expression here, which is 2 to the power depth of T plus 1 minus 1. Now, since the set of perfect binary trees is defined inductively, we're going to write a proof by structural induction. Always remember to start with the basis step, which is to prove the property P for all the trees that are produced by the base rules. Here there's only one base rule, that's R1. So let T be any perfect binary tree that is built by R1. What's the total number of nodes in that tree? Well, of course it's 1, since all the trees produced by R1 are single node trees. And then let's compute this expression. The depth of T by definition is 0, so this expression is equal to 2 power 0 plus 1 minus 1. And of course that's equal to 2 minus 1 equals 1. The fact that these two numbers are equal concludes the proof of the basis step. Now let's write down the second subproof, namely the inductive step. Let T denote any perfect binary tree that is built by rule R2, which is the only inductive rule in the definition of the set. Remember that in that rule we use two existing trees and we denote them by L and R, which are the left and right subtrees of T. So by the inductive hypothesis, the property in theorem 3 holds for both L and R. And now we must prove that this property also holds for T. So we're going to compute the total number of nodes in T, and according to rule R2, that number is just the total number of nodes in the two subtrees plus 1 to include the root node of T. So here is the expression for that number. Now we can use the inductive hypothesis to replace n of L by the corresponding expression in theorem 3, which is 2 to the power d of L plus 1 minus 1. And then we can use the inductive hypothesis a second time to replace n of R by the corresponding expression. And don't forget to justify in your proof by structural induction the step when you use the inductive hypothesis. Here we use it twice. Now let's look at this complex expression and try to simplify it. Well, the first thing to realize is that this number, depth of L, must be equal to the depth of R because this is a constraint that is stated in rule R2. The two subtrees must have the same depth. So in other words, this expression here is equal to that expression here. Therefore, we can rewrite it as 2 times this expression plus 1. Now, we're not quite there yet, but we're pretty close. The next step is to realize that depth of L plus 1 is nothing but the depth of T. Remember that in rule R2, the depth of the new tree is 1 more than the depth of its subtrees. So we can replace this expression here by d of T to get this expression. And then we just have some algebra to do. We can multiply out the 2 to get this. And of course, this expression is nothing but 2 to the power d of T plus 1. This is just minus 1. And this is the expression that we were looking for. In other words, this concludes the proof of the inductive step. So together, the basis step and the inductive step complete the proof of theorem 3. Now, in general, when sets are defined inductively, their definition may contain more than one base rule and more than one inductive rule. So when that's the case, you must make sure that the basis step covers all of the base rules and that the inductive step covers all of the inductive rules. And we're going to see an example of such a definition in the next segment.